All right, we got lesson 2.2.2, rates of change, day 2. All right, so what we're going to look at today is rates of change don't have to be like speed, like meters per second that we were doing before. There's a whole bunch of different stuff that rates of change could be. So the first thing I've got is I got 3 different graphs describing 3 different situations. Okay, what we want to do is describe the real-world quantities of the graph and then calculate the unit rates for each of the different situations. So unit rates don't always have to be meters per second or miles per hour or things like that. It can be a lot of different things. So on our first one, when we're looking at the description, the first thing that we want to look at is we want to look at the x and the y axis. So in this case, the x-axis is the years since planting, so they're planting something, and then we're counting years, and then the height of the tree. So if I'm looking at this, my change in y over the change in x, the slope or the rate of change, is going to be the height of the tree over the number of years. In this case, we're doing the height of the tree in feet and years in, well, time in years. So we've got height per year is really what we're looking at. So this one, since it has an intercept up here, what does that tell us about the tree? Well, if it starts here at the year 0, it means this tree started off at 4 feet tall. So we're not looking at like a seed planted in the ground. They went to the store or something, got a tree, and it was already 4 feet tall when they planted it. So that's what that's saying. And then it starts increasing its height, which makes sense. You wouldn't expect the tree to decrease. So as years go by, it gets higher. Okay, and so what we want to do now is calculate the unit rate for each of these situations. So if we're going to do the unit rate, we're going to do the change in the y divided by the change in the x. So this other point here was at 0.4. So let's look at our change in the y value, the change in the height in feet of the tree. It went from 4 feet to 14 feet. That's a change of 10. And you could do it just by taking 14 minus 4. That's a positive 10-foot increase. Now what we want to check out is what was the change of x during those 10 feet that it was growing. Well, it went from 0 years to 5 years. So 5 minus 0. So we're looking at 10 feet for every 5 years is the growth of this. But we want to look at unit rate. Unit rate isn't for 5 years, it's for 1 year. So what we're going to do is reduce this fraction, and we get 2 feet every year. So 2 feet for every 1 year, and that's its unit rate for that situation. All right, the next one, do the same thing with these next 2. Okay, so you've got this next one, time in months. Okay, and we're looking at bank balances. Next one is gas in gallons, and we're comparing it to the number of miles that is driven. All right, so I want you to describe the quantities of the graph and then look for those unit rates in those situations. Okay, I'm going to pause it, and then we'll look at my answers to check out yours. All right, 5, 4, 3, 2, 1, pause. And see how you did. So in the first situation, it looks like we have a bank balance, and then over time, look at how this graph is going. It looks like our balance is going down because we're spending money. So we've got our bank balance is going down. So since this slope is going down, we would expect that our unit rate would be negative. And in fact, it is. So we're looking at dollars per month, and it looks like we are losing $20 every 2 months, so that's $10 per month because we want the unit rate, which is per 1 month. Not $20 per 2 months, it has to be $10 per 1 month because unit rates are always in like 1 month increments or 1 year increments or something like that. So that's why this one is decreasing here. For the next one, we're looking at, looks like some type of vehicle, and it's got its gallons and its distance. So we're looking at miles per gallon for this one. So we want to use our unit rate. This one's increasing, so we expect to see a positive relationship between miles and gallons. And we end up with 44/2, but that's not the unit rate, because this is 44 miles for every 2 gallons. We want to know how much it is for every 1 gallon. So we reduce it, and we get 22 miles per gallon. That's the unit rate, 22 miles for every 1 gallon. All right. Now, on these, you can think about it, and do any of these look like they might be able to have a negative y value? All right, so all of these are in the first quadrant, but could any of these actually have a negative y value and maybe go down into the fourth quadrant down here somewhere? Well, this one, if we go negative, that means we're going back in time, so that's probably not going to be one to work with. This one, you can't have negative gallons of gasoline in your gas tank or go negative miles, so that doesn't make sense. But on this one, where we got time in months, maybe this one could go below, because it's possible to spend more money than you have, and then you end up owing the bank money. So this one, maybe it's possible for later on to see that we could have a negative y balance at some point where we owe the bank money because we use too much. All right, let's move on. Next section. All right, so let's say that we've got this motion detector. So we've got a motion detector saying toot toot toot, so it's detecting motion. And then you've got a person over here. Yay! So there's a person. And maybe this person is going to walk towards the motion detector. If they're walking towards the motion detector, the distance is going to go down, and then it's going to take a certain amount of time to do that. So they might walk towards it, or they might walk away from it. So that's what we're looking at, is we've got some kind of motion detector set up there, and we've got somebody walking towards it or away from it. So in this situation here, we've got somebody who was in front of a motion detector, and then they walked toward, they were walking around, and the motion detector is telling how far the person is from the motion detector, and also recording how long, over what time period this is occurring. Okay, so if this is a motion detector situation, describe the situation. Now what we have here is what's called a linear piecewise graph. Piecewise graphs are graphs that are made up of multiple different functions. So we can see here that there's actually 3 parts to this. There's 3 piecewise parts. We've got a decreasing section here. We've got a constant section where the y value does not change. And then we have an increasing section for that. So in terms of the motion detector, what's happening here is going down decreases means you're getting closer to 0, which means you're getting closer to the actual motion detector. When you're not, when you've got a constant section, that means you're not moving towards the motion detector and you're not moving away from it. And then this section here shows us increasing our distance from the motion detector. So that's when we're moving away from the motion detector. All right, so describe the situation. So how would you describe this piecewise graph in terms of it being a motion detector? Think about that. How would you describe what's going on here? Talk about where they start. Do they move towards? Do they move away? What about that section where nothing's happening there? And then what about the other one? Talk about their rates of change too. How are the rates of change different? Okay, think about it. I'm going to pause for 5 seconds or a few seconds. 5, 4, 3, 2, 1. All right, so hopefully you wrote something down. If not, then pause and write something down real quick. But let's write down some things that we noticed here. Well, we're always going to start with the starting point. So it looks like at time 0, they start 5 feet away from the motion detector. Because right here at 0 feet, that means you're at the motion detector. And that's for the y-axis. Time is on the x-axis. So we would say that we start 5 feet away. All right, and then it looks like we get to the point where we're 4 feet away. And how long does it take to get there? Well, it looks like it takes 4 seconds for us to get 4 feet away. So we're only gaining a foot there. So they walked really slow here. So they walked slow, oh no, sorry, towards it because they're getting closer. They went from 5 feet to 4 feet. So they walked towards the motion detector slowly. So the next section is walked towards detector slowly. I really misspelled detector. Detector slowly. So what did you say this section represents? It looks like they just paused for 2 seconds. Okay, so then we'll say they stood still for 2 seconds. And then let's look at the next section. At the next section, it looks now like they've turned around and they are going, let's see, 1, 2, 3, 4, 5, 1, 2, 3. So they're going 5 feet every 3 seconds in the other direction. All right, so they move away at a faster pace than this pace right here, because you can see it's a steeper line. So that means it's a higher rate of change. So our last thing that we're going to write there, what did I say? We're going to write that they walked away at a faster pace. All right, now I want you to write equations for each section of the graph. So we want to write an equation for this section of the graph, this piecewise. We want to write an equation for this section of the graph, this part of the piecewise. And we want to write an equation for this part of the graph. All right, so we got 3 different parts of the graph. I want you to write equations for those 3 parts. I'm going to pause right here. 5, 4, 3, 2, 1, and then you can check your work. All right, so here's my answers. I've got for the first one, y equals negative 1/4 x plus 5. I've got a negative slope on it because we see in the slope triangle that it's going down 1. So it's decreasing in feet for every 4 feet or 4 seconds. And we started at 5. So I started at 5, so it's negative 1/4 x plus 5. The next one is a constant. So the y value is not changing. The y value is always 4. So that's why I wrote y equals 4, because no matter what the x value is, the y value is 4. Next one, I got 5/3 x because of the slope triangle here. It's increasing by 5, and then the x value is increasing by 3. Now, how did I get the -6? Well, you can keep on following back your slope triangle. So if I go back 3 spaces and then go down 5, well, that's 1 below this, so that's -1. If I go back 3 more, I'm going to go down 5, so that's -6. So at -6. So you go back 3, you're at -1. Go back another 3, and you're at -6. So that's how I found out that one was going to be -6. Now, normally, if you were doing a linear piecewise graph or function, you would write it like this. So this says y equals, and then what does y equal? It equals all this stuff. Well, here it says y equals negative 1/4 x plus 5, but only from 0 to 4. So that means from x value of 0 to an x value of 4, that's when it behaves like this function. And then we change to a constant graph, so the next one is y equals 4, but that's only between 4 and 6 for the x value. So from 4 to 6, we can see here that it's behaving like a constant, where y is equal to 4. Well, once we get to 6, it started behaving like this other graph here. So that's 5/3 x minus 6 when x was greater than or equal to 6. And that's when it behaved like that. And that would be a piecewise function. All right, we are almost done. We're getting there. Next part. All right, so we're still on that motion detector. So remember, we're talking about the feet you are away from the motion detector and time. Both of these are impossible for the motion detector. So look at them and then explain to me why they are impossible. Okay, I'm going to pause it here and we'll give you a second to check them out. So pause your screens real fast and we'll try to figure out why these are impossible. All right, let's see what you got. So for this first one, this one doesn't make sense to me because it looks like time has stopped here. So it looks like we only have one specific time. Oh no, maybe call this like 4 seconds or something like that. So at 4 seconds, now look at this. I've got multiple distances. So what is this saying? It's showing that we're in multiple places all at the same time. And on top of that, time has stopped. So that one makes no sense as far as the equation for a motion detector would be concerned. Because we would expect to see time to have different times and then be in different places during those times. The next one has some teleportation going on here. So we're at this distance, and then all of a sudden we're at a different distance. Then all of a sudden we're at a different distance. So there's teleportation going on there, which we don't have the technology quite yet for that. So that can work. And also, look at this spot here and this spot here. For the same time, we're in 2 different places at the same exact time. And that's probably not possible to be 2 places at once. Sometimes your schedules are like that, where you have to be at 2 places at once, but it doesn't really work out very well. So we got you at 2 different places at once, and teleportation, boom, all of a sudden we're at a different distance. Whereas if this were a discrete graph, we should see some kind of line connecting time and distance there. All right, so that's all we got for today. We've got a couple more things to cover. We've got a learning log that I need you to write. I want you to create your own situation. So it has to be something original that has a rate of change in it. Kind of similar to one of these 3 things that we did here. So don't necessarily just do like a speed, like meters per second or feet per second. Come up with something a little bit more interesting. Surprise me, wow me, please. All right, so write one out, sketch the graph. So sketching the graph doesn't mean you have to have an exact graph. It can just be you really quickly going, okay, boom, boom, there's my axis. And I want you to label your axis. So you'll label your axis here. Then you'll sketch the graph, and maybe you'll do a decreasing graph because those are interesting. And then you'll tell me what's the explanation for your graph. Okay, so what's the rate of change and the explanation for your graph. So be interesting. Don't just do things that we've already done. All right, the last thing we've got today is kind of some review, just kind of some of the concepts, make sure that you're getting them. So for our methods and meanings, we've got writing equations of the line. So first of all, we have to remember that the equation of the line is always in the form of y equals mx plus b. Well, it's not always in the form. That's just one of the forms we use. So this is called slope-intercept form. M is the slope and b is the y-intercept. So if I've got a graph, I can easily find the slope by using a slope triangle. And I can see that this is 1 over 3. So it's increasing by 1 as the x is increasing by 3. So our slope is 1/3. And we can see that our intercept right here is 2. So it's 1/3 x plus 2. So if you have a graph, it's pretty simple. As long as they're crossing at nice round numbers, it's pretty simple to find your equation. So you can go from graph to equation. You could make a table if you wanted to, but you don't have to. Okay, so you could also, if you have the equation, go directly to a graph. You don't have to write out a table and then go table to graph. You can go straight from an equation to a graph. And so they gave us an equation here of -3/2 x plus 4. So we started going up 4, and then the slope is -3 over 2. So we go down 3 and over 2. So we just use our slope triangles to find the next point. And you can keep on doing that, down 3 and over 2, and find more points. So you don't need to go from an equation to a table and then to a graph. You can go from an equation straight to a graph. Okay, and finally, you can get an equation from just looking at a table. You don't have to graph this in order to find your equation. First of all, I see 0, -4. That's the y-intercept. So I know the y-intercept is going to be -4. So it's going to end with -4. And then all you have to do is find out your rate of change. So it goes from -4 to -3.5. So it looks like it's increasing by 0.5 for every 1 here. So 0.5 over 1 is 1/2. So our rate of change would be 1/2. Okay, so what we really want to be able to do by the time that we're done with all this is you can start anywhere and get anywhere else you need be. For instance, you can start with an equation and you should be able to go directly to a table, or start with an equation and go directly towards a graph. Or I can give you a situation and then you can be able to go directly to a table from that situation, or directly to a graph, or directly to an equation. You know, any one of those table, graph, equation, and situation, you should be able to move from one to the other effortlessly by the time we're done with this unit. All right, so that's all I got for you. Make sure to write down the methods and meaning stuff to make sure that you're understanding our information, and there will be stuff like this on the homework. All right, thank you very much. We are done with 2.2.2. Bye-bye.